Hi there, welcome back to the channel. Welcome to another video in the Back to Basics series. This time we're going to handle RF alignment, specifically RF alignment of the AM bands. This radio has a few peculiarities. It's slightly different to some of the other radios, but the concept is the same. The theory is the same, and the way you go about it will be something you have to sort of adapt as you go along, depending on what kind of radio you have in front of you, because in most of these sets, there's always something slightly different. Either it's designed differently or the instructions tell you to do it a different way. The whole point is, regardless of what they tell you to do, it's incredibly important to know why you're doing it. If you know why you're doing it, you won't get baffled by the instructions. You'll know exactly what they're trying to get at. And that's the whole point of the series, that you know why you're doing something. The doing is quick. Most of the time, it's incredibly easy. The understanding, the explaining takes a hell of a long time, which is why these videos sometimes get spread out a bit more, both in time and in duration, in length. But I'm going to do them anyway, and I'm doing them anyway because a lot of you are asking for this sort of thing. And I'm glad to know that I've actually inspired some people to get into this hobby with a different outlook, with more understanding, rather than simply following instructions. This is a hobby that can be incredibly dangerous if you don't understand what you're doing. You're dealing with high voltages. So as most of the creators I watch say, you're doing this, if you're working on this, you're doing so at your own risk. The whole idea is to minimize that risk. So I do hope that if I save you, at least even one of you, from getting zapped, I've achieved my goal. So if you've been following the series, if you enjoy this sort of thing, stick around and enjoy the video. But before I carry on, I just want to thank the sponsors of the video, PCBWay. You'll find them at PCBWay.com. They're the people I go to for all my PCBs that I use on my channel, and the projects that I design I make available on the share section of the PCBWay website, where you can just go there and order boards directly. Right now, they've started their PCBWay 10th anniversary tour, which allows you to enjoy a personalized experience in this interactive section of the website. It'll give you brief history of your own experience with them. It'll make available some coupons for you to use on the website and a lot of other goodies that will make your experience even more enjoyable. They've also got a charity badge sale if you want to participate. And of course, you'll also be eligible for a lucky draw. So whether you just want to order PCBs or any one of the large number of other services they provide, visit PCBWay.com, participate in the 10th anniversary tour, and I'm sure you'll find something for your needs. The RF alignment of a radio has a hell of a lot to do with the dial glass, and we've got a bit of a problem. If you recall from the first video, the dial glass was completely shattered when it arrived. But fortunately, thanks to this rather amazing community that we have here, someone sent me a brand new dial glass. Well, brand new, it's about 70 years old or 60 years old, but it's in perfect condition. And here it is. It arrived incredibly well packaged with a sheet of plywood in the front and back, everything taped together nicely. Got through without being damaged. So now I can put it on and we can do the RF alignment. The dial glass is on. I haven't screwed it all in because I will be removing it again to clean the radio, but I need it for the RF alignment. And I noticed something interesting here, which I hadn't seen before. I was looking for the marker points for the end of the dial, and I found this. I hadn't seen it on this radio before. It says Draakfunk over there. This is the long wave dial. You see 150 kilohertz there, 200 there, but you also see these numbers over here. You see 1, 2, 3, and so on. And I sat there looking at that, thinking, what the hell did they do that for? And I realized this thing had wired radio function. When these radios came out, I think they were still using that wired radio where they'd actually send radio stations across a telephone line. So you would tune in to, well, the wired stations, 1, 2, 3, 4, however many there were in your area. And I believe these came over the phone line. I'm not quite sure where you plugged it into. Usually you had a separate input for this, but yeah, that's just something I found by the way. But the reason I was looking at this end is because I wanted to see whether the dial pointer, which is over here, you can see it moving inside there, whether that was aligned to the end of the dial. Now, these dials have a little marker here, and I'm trying to see if I can detect it. You see that kilohertz sign there and that kilohertz sign there? There's actually a little blip over there. Now what you need to do is before you start doing any alignment, you've got to adjust the dial pointer. You see where it is over here? You can move this left and right. You just slide it on the guide wire till this marker on the inside there lines perfectly with those little markers on the dial. Now, from the angle you're seeing it, it looks like it's off, but from where I'm seeing it, it is perfectly aligned. So that's the first thing you need to do. This is important because if you're going to align the frequencies to the dial or the pointer to the frequencies you see on the dial, and if it starts off wrong, you're wasting your time. You've got to get it right at the beginning so that it'll track correctly across the scale. Now in this case, I don't have to do anything because it is perfectly aligned, but usually I do adjust somewhat. And one of the reasons you need to do this is if this dial pointer is out by 1 centimeter, let's say to the left over here, and let's say that you're tuning to 150 kilohertz and the pointer is actually there, it might also be equally off on this end. So when you're tuning to say 350, the station might be on 350, but your dial pointer might be over there. If you do get that and you see that the distance, the error in terms of distance on this side is the same as on the other side, then you know your dial pointer is out and your alignment's probably perfectly correct. So that's the first thing you need to do, or you could waste a hell of a lot of time. So what exactly are we trying to do? We are trying to ensure that when we dial into a frequency that we know, for example, if I'm listening to medium wave and I want to listen to a station on 1000 kilohertz, so 1 megahertz, there's my scale over there, medium wave. There's 1000 kilohertz over there. So if I tune to that, now my pointer is perfectly aligned to the 1000. I want that station to come through when my pointer is aligned to the 1000. If it's not properly aligned, then if I know my station is at 1 megahertz, 1000 kilohertz, and I pick it up there, then my alignment is off. I could also pick it up there and it's off the other way. So I want to align it there. What I also want to do is I want to make sure that it tracks across the entire dial. So if I've got a station up here at 1600 kilohertz, I want it to align there. And I also want it to align at the other end, say over here, where there's a station that I know at 550 kilohertz. So I want this thing to track properly across the entire dial. I want it to be optimally tuned so that the signals come through as best as they can from the antenna at those frequencies and also at those frequencies. And I want to make sure that it's more or less accurate across the dial as well, because sometimes it isn't precise. And I want to make sure that I can do that for the medium wave, the long wave, the short wave, and the FM. Okay, let's have a look at this graphically because it's probably easy to understand that way. So we're back to the drawing board. And the drawing board here consists of the AM front end. This is the RF section. This is the oscillator section, which I explained previously. These two feed this ECH81, which is a mixer oscillator. But for the purposes of the RF and oscillator alignments, we don't need to look at this. All we need to know is that 460 kilohertz IF frequency is going to come out of there when this whole thing is working well. 460 kilohertz is that IF frequency that we've talked about before, and we know how it's generated, and we don't need to look at all this because it just confuses the issue. So let's get simpler. And this is really the only part of the circuit that we're interested in, the RF front end and the oscillator section. Now, remember, this thing is working for long wave, medium wave, and short wave, depending on how these switches are operated. I'm going to look at the medium wave first. And let's put in the switching that affects the medium wave so we can see exactly what it is that we're tuning. This is what we are left with when we get rid of everything that does not have to do with medium wave. And I've also done things like simplify the drawing, remove the switches. It's usually that kind of detail that distracts us from what the circuit is doing. And I found that if you can simplify it, it makes it a lot easier to understand. And I think this is as simple as can get. I mean, I could draw the capacitors differently, but essentially this is what you have on that front end and on the oscillator. And if we want to see them more clearly, we can do this. This is the RF front end, the antenna circuit. The antenna is over here. And this is the oscillator section for the medium wave. Now remember, the oscillator section requires the ECH81, but this is what we are looking at when we're looking at the alignment of it. And we can look at these separately to see how it is that we are going to affect the tuning or the alignment when we start following the instructions they give us. Essentially what we have here are two tank circuits, tuned tank circuits. Now, why do we say that? Well, this front end circuit has an inductor and a capacitor. I say a capacitor because while you see two capacitors here, they are both connected to ground on the one side and both connected to this point on the other side. So these capacitors are effectively in parallel. They sum together to make the effect of one capacitor. And here it is. Here's our inductor, which is adjustable, tunable. And here is the capacitor made up of two capacitors in parallel. This one is variable. This is half of the tuning condenser on our radio when we tune the station. And this is a trimmer capacitor, which we can adjust, but then we adjust and forget it, okay? That is our tuned circuit. Now, this produces a filter response at the front end focused on the station, the particular station that we want to listen to. And then we've got this section here, which is also a tuned circuit, a tuned LC circuit. There's our L, which is adjustable, trimmable. And here is again a capacitor made up of two capacitors. One is the other half of the tuning condenser that we tune our radio to. And this is again another trimmer, which we can use in conjunction with that one to make the respective or necessary alignments. Right. Now, this displays effectively the characteristics we're looking at. A tuned LC circuit at the front end, where we have a variable tuning provided by this half of a tuning condenser, and the tuned LC circuit in the oscillator, which again allows us to tune with that half of the tuning condenser, and therefore makes it possible to vary the frequency of this oscillator. These two circuits are actually different. One is an actual frequency that I'm tuning to, or creating by adjusting the tuning of this tune circuit, and the other one is actually a band pass on a filter that I'm creating at the front end. Now, let's first look at something else. If we look at the formula that guides us in calculating the resonant frequency of an LC tuned circuit, a tank circuit, this is what we have. The resonant frequency is equal to 1 over 2 pi times the square root of LC. Now, this is the important thing here. The L and C are under the line. In other words, the frequency, the resonant frequency, is inversely proportional to both the inductance and the capacitance. What does this tell us? And why is this important? Well, it's important because the one tunable, not adjustable, tunable element that we have in both of these circuits is that capacitor over there. There and there. They tune together, but they are variable, right? Which means that we have two extremes of FR, resonant frequency. The one extreme is when the tuning condenser is completely unmeshed. So when you tune it all the way to the one side and you have the minimum, the least capacitance being provided by that tuning condenser, right? Least capacitance there, least capacitance there. Now that gives us a top end frequency, because the lower the capacitance here, the higher the resonant frequency, because it's inversely proportional, right? So if you put that at zero, right, zero capacitance, 0 picofarads, usually these are about 0 to 300, but they don't quite go down to 0. They're more like 10, 12 picofarads at minimum, depending on the tuning condenser. But if you put that at its minimum, what you want from your frequency here, in this particular case, in the antenna circuit, is you want this FR to be the top end of your scale. In other words, on medium wave, you want this FR to be about 1650 or whatever it is. I think it's 1650 kilohertz, the top end of our scale. If that thing is fixed at minimum, you can't go lower than that, right? Then you got the other adjustable element here, which is the L. And that's that guy over there, the L. Okay, so you can adjust the top frequency by adjusting the L, because you can't adjust this any further, right? It's at a minimum. You can adjust the L. What you can also adjust is this guy here, because there is some capacitance. But usually what you want to do is put this around halfway so that it gives you some flexibility up and down. So if this is usually about 30 picofarads, up to maximum 30 picofarads. So if you leave this at 15 picofarads and you've got this one down near 0, you can set that to give you 1650. Then if you look at the opposite extreme, where you've got this thing on maximum, it means the frequency is at minimum, and you want that at about 550 kilohertz, whatever the minimum is, You can also adjust that slightly because you can do it by adjusting L and C, the total C, because you've got that trimmer there, but you can also adjust that. So what you need to do is you need to adjust the one end and the other end. The one end is when your capacitor is at a minimum, and the other end is when your capacitor is at a maximum. You've got these two tuning elements to allow you to shift that filter one way and the other. And what you're going to get is a frequency, a center frequency, which is what you desire to pick up your main station, the one you're listening to best, but it won't be a sharp curve there. It'll actually be a bell curve like that. Typical bell curve, because all it is it's a band pass filter centered on the frequency of your station that you have tuned to with that guy there, right? When you turn the dial. Now, this front end frequency is not absolutely sharp. In fact, some of them are very, very relaxed. I mean, it can be something like this. It can be pretty wide over there. What it means is that if you are listening to that frequency and you're tuning to that frequency, it might actually be slightly off tune and you still get almost the full strength of the signal. But what you really want to do is you want to be able to center the peak of that band pass, of that curve, of that bell curve, right on your frequency. Now, what is this frequency? Well, this is where the oscillator comes in. Now, the oscillator, also being a tuned circuit, works differently because what it does do is it creates a very sharp frequency, a frequency which is usually the IF frequency higher than the frequency that you want to listen to. Okay, these two Fs are not the same, right? They're just, they were used to indicate frequency, but they're not the same. If that is 1 megahertz, that is 1.46 megahertz. So the actual station that you're going to listen to, that you're going to hear, is more a question of where this is tuned to than where that is tuned to, because that is a band pass and this is an absolutely sharp frequency. Okay, that's what happens when you get this thing going through. This frequency sets what you're going to listen to. Let's try and follow this logically. If this thing is set to 1460, and it's a very precise frequency, there are a few sidebands because there is a little bit of distortion, obviously. Now, that gets mixed or fed into your, created and fed into your mixer oscillator. Now imagine at the front end, you've got this situation where you've got that slap bang on there. Now what frequency is going to go through there? All these frequencies are going through there, going into your front end. Obviously the ones within this band pass are slightly stronger, but because your mix is creating a difference, a subtraction of that from that, so 1460 minus that, you can get various figures, because if you look at this frequency above here, it'll give you a different amount. It'll give you 455. That one there will give you 465. That one there will give you 460. And why does this one go through? This one goes through because that's what you've tuned your IF filters to. Your IF filters determine which IF frequency goes through, because a lot of IF frequencies are created. This F, this 1 megahertz station, is not the only one going through. You know, the signal coming in at, 9 kilohertz above, 9 kilohertz below, they're also going through. They're also getting mixed into your mixer. But the one that your mixer irons out, selects out, is precisely the IF frequency that you've aligned that filter to. So it'll only allow 1 meg to go through because it's 1460 here, minus the IF frequency that you've tuned to will give you the resulting frequency that'll go through there. Because you can have 1460 here, right? Your IF filters are all set to 460. So it's listening for 1 megahertz. And if the station you're listening to is at 1 megahertz, but your filter here, let's say you've got this really poorly tuned at the front end, your filter here is like that. It doesn't mean it's going to pick up that station over there. It's still going to pick up this station over here, albeit rather dampened or weakened, because your front end is cutting off part of the power that would otherwise come through if that thing was perfectly aligned like that. So here's the logic. Your front end curve or filter can be sharper or broader. It'll still work. The sharper it is, the more focused you are on that frequency and the more selective you become, because you cut off the adjacent frequencies to the one you want to listen to. And it is determined by two things, not really by that front-end bell curve, but more by the frequency that you're generating here, which is a very specific frequency, which is adjusted, again, tuned at the bottom end of the range and the top end of the range by these elements here. This is the trimmer to add to that capacitor, and this is the coil that interacts in that formula to give you the actual resonant frequency. So you've got to tune them at the bottom end of the scale and the top end of the scale and try and keep some sort of linearity in between, so that although you're tuning, let's say you adjusted at 550 kilohertz at the bottom end of the scale, and you adjusted at 1.55 megahertz at the top end of the scale in terms of frequencies, at 1 megahertz, you still wanted to point generally to the 1 megahertz point, right? You do not set it to 1 megahertz and hope for the best at the ends. You set the ends and really hope for the best in the middle. That's the essence of an RF alignment when you're doing it on a radio like this. So essentially what you've got is you've got a frequency scale here, and let's say you want to listen to that station of yours, your favorite station, at 1 megahertz. There it is, 1000 kilohertz. What your local oscillator is going to produce, and which you adjust for, is 1460. The reason you adjust for 1460 is because your IF chain has been tuned to 1460 to allow 460 to go through. That's your IF frequency. Your IF transformers and your whole IF chain has been focused and tuned to 460 kilohertz. So when you produce 1460, the frequency that you're going to be listening to on the frequency band is 460 below this frequency. So you're going to pick up 1000 kilohertz. The IF being produced is this one down here, 460. Now, if you tune this wrong, if you tune the IF frequencies wrong, this will shift. This won't be 460. It could be 455, 450, could be 465, which means that if you don't align this, you no longer will pick up that 1000 kilohertz, because the curve will change of what it is that you're picking up at the front end. I hope that's easily understandable. Essentially, because you've tuned your IF chain, your IF transformers, your IF amplifier to a particular IF frequency, in this case 460 kilohertz, you are now going to align the oscillator to exactly that frequency above the station you want to listen to. So when you put the dial at 1000 kilohertz, you want the oscillator to produce 1460 kilohertz, so that your station at 1000 kilohertz, the information that's being communicated in that station, will appear on the 460 kilohertz IF frequency, which then is allowed to go through the signal chain. All right. Whew. Enough explaining. Let's get to some doing. Right, after all that blabbering, it's time to do the actual alignment. And this is the thing about these radios. The theory is the most complicated part to explain. The actual doing is very simple. And obviously it's simplified when you know the theory, which is why I went into the entire description. But let's get started. We looked at all the detail on the medium wave, and that's precisely where we start with the RF alignment. It says medium wave on here. So the first thing is we'll click medium wave, and it tells us to set the dial all the way to the right to the 515 kilohertz mark, which is that little guy over there, little blip on there. It doesn't have 515 marked on it. The first mark is 550. Now be careful, this thing's got meters and frequency. The top is meters, the bottom is frequency, and this is deceptive because at 550 kilohertz, it's actually 550 meters just to the right. So we've got to look at the bottom dial. We're looking at kilohertz frequency. So 515, that's that little blip on the right. And if you haven't got that adjusted, the pointer adjusted, you should adjust it to there just by moving it to the top there on the guide wire. And then it says at the mark of 555 kilohertz, you have to adjust an oscillator and a front end coil. Now, first of all, we need to send the signal, right? Let's set that up. I'm going to set 555 kilohertz on the signal generator, and then I'm going to set the amplitude to the minimum. I'm going to give it modulation. It'll be AM modulation. We'll leave it at 50%. and let's give it a 800 Hertz tone. And we've got that signal coming out of there. So we've got ourselves a faux radio station sending a signal at 555 kilohertz. If we tune to 555 on the dial, we should be able to pick up that tone. Now I've got it going into the switcher here, the attenuator. I'm not sure that I'll need that because I'm using a different method to inject the signal in here. And this works well on long wave and medium wave. And that is by actually using the ferrite antenna. So we don't actually have to connect this to the antenna sockets at the back, which is what you can do as well. But I prefer to do it this way. Let me show you. I've created this coil of wire. It's about 5 turns, and I've got the signal coming into here. This is just creating a coil, like an antenna that's going to radiate the signal. And then what I do is just place it on here somewhere near the ferrite antenna. There's the ferrite antenna, and I should be able to pick it up. Actually, you should put it directly in line, but it's not necessary. I've got the signal at minimum strength at the moment, and we'll see if we can pick it up. So let me go to the dial and try to tune to 555 and see how close this thing is. The advantage of using this is that you're not loading the antenna at all. Remember, you're going to be adjusting an antenna coil as well. And when you adjust an antenna coil, it's going to take into consideration the actual impedance coming into the antenna. So because my signal generator is 50 ohms, it would actually throw it off. However, I've actually got an antenna switch on here. It's a dummy antenna on the attenuator so that I can make this thing look like a proper long wire or external antenna. However, I still prefer the coil method. Let's go to the dial. Okay, let's give it some volume. Yeah, I can hear that. Let me tune. Remember, I'm right at the end here. There's 550. There's a little blip over there on 555. And there it is. Now, if I move the ferrite or the coil in line with the ferrite, you can see it goes up, but I don't need it to be too strong. I can hear it perfectly, and this is incredible. It is, put the volume down. It is exactly on the blip, and I haven't changed anything. However, I'm going to flip this over, and I'm going to make some changes so you can see this thing operate. This isn't fair when you try and do a demo and it doesn't require any work. Let's just, out of curiosity, go to 1 megahertz and see how far off we are. I've set the signal generator to 1 megahertz. And where's 1 megahertz? It's over there. It's a little bit off. That is 1 megahertz. It's on the last 0, so it should be a little bit to the left, which means that our alignment on the left-hand side might be off. Okay, let me flip this over and we can make some adjustments, and I'll show you how the adjustments affect the alignment. We're only looking at the oscillator at the moment. We're only making sure that the oscillator is putting our signal flat on the band. We haven't touched the antenna circuit, so I don't know whether that's going to increase the amplitude or not, but we'll be able to see all that. I've connected an AC voltmeter to the output of the speaker. It's actually going through my little multiplier here because it doesn't actually produce enough voltage to give us a good swing on the meter. Speaker's got a speaker or dummy load option, so I can get rid of the noise if I don't want it. Now what I've got is 555 kilohertz coming in, which is what they tell us to set it to. So 555 kilohertz. Let me put the volume up. We can hear it. And I'm going to tune exactly to 555 on the dial. As you can see, I'm rocking it past 555 on the dial, and it's exactly there now. Let me put dummy load on so we don't have to listen to it, and I can put the volume up till we get a decent deflection on the meter. This is actually pretty loud and annoying. So dummy load is on. Now what it tells us to do is to adjust oscillator coil A and the front end coil C for a maximum. And we know from the schematic where A and C are. And if we look on the underside, this is A over here, and this is C. So I'm going to put the volume up just for clarity. We're not looking at the peak at the moment. We just want to hear the tone. And A is the oscillator coil. So this one over here should change our tuning on the oscillator from the 555. Remember, 555 is what's set up there. See that? Passed and passed. Now I'm going to leave it at the peak, which is where it's perfectly tuned to 555. Now what I need to do is I need to peak the antenna coil at 555 as well. Now this is where that comes in, and that's important. So I'm going to put the dummy load on, give it a decent deviation, and I want to peak that. And that is my peak. And that's it. What I've done now is I've adjusted the oscillator so that the 555 signal coming in shows precisely at 555 on the dial, and the antenna circuit is precisely tuned to allow that signal to go through optimally at 555. Now it tells us to set the oscillator to 1480, and I'm going to do that off camera, 1480, and I'm going to put the sound on again, and now I'm going to tune it to 1480, which is, there's 14, there's a little blip on the dial there, which corresponds to 1480. It's slightly off, so I'm going to put it exactly at 1480 over here. I'm looking at it straight on. Now they tell us to adjust the oscillator trimmer B and the front end trimmer D, and we again know from the schematic that those are this one and this one. I need a better screwdriver for that. Again, these are insulated. So I'm going to do the antenna. Remember, I've put it on 1480. Just checking. And I need to optimize that. Actually, B is the antenna, is the oscillator. See that? There's my optimum. And now I do the front end, and this is where that comes in. Let's put the dummy load on. This is to peak the front end coil or circuit. I got a bit out of that. Actually, good Lord, I got a lot out of that. What happened here? Why is this so different? I'm still using that coil, so this is the best way to do that. And I've really improved reception on here. Now the question is my 555 still correct? This is the problem with these things. You've got to go backwards and forwards quite a few times to make sure that you haven't messed up the one side, because each one affects the other. So off camera, I'm going to give it 555. I'm going to go down to 555. Actually, it hasn't moved it at all. Magically, this one hasn't affected it at all. So what have I done? I have adjusted the frequency at the low end of the frequency band, 555. I've just moved it to show you how it's done by moving that oscillator coil. It didn't need any adjustment, but you saw it going backwards and forwards. I peaked reception at that point by adjusting the front end, the antenna circuit coil. So we optimized it at that point. And then I went to 1480, 1450 was it? At the other end of the dial. And I had to adjust the oscillator by adjusting that guy there. And then I peaked it by adjusting that guy there. And you saw we got quite a big difference. And that is my RF alignment of the medium wave band. So if everything has gone well, we should have more or less optimized that whole dial alignment and front end reception of, or the antenna circuit of the medium wave. Let's test it on 1 megahertz again and see where we are. So now let's set the signal generator to 1 megahertz and we'll see where we are on the dial. There's our 1 megahertz line over there. Okay. it is not absolutely on. That's the peak. Let me drop the volume. And this is where we start seeing some of the anomalies that you get on these radios. We've aligned it to 555 over there precisely. We've aligned it to 1480 over there precisely. And then the frequencies in between are close. They're not absolute. And the reason is that, well, the linearity of that tuning condenser might not be precise as well. And you can actually adjust it. There's little fins on the side that you can bend out to try and improve the alignment. Believe me, it's not worth it. Let me show you on 1200, see what we get. So 1200 kilohertz. Still a bit shifted to the right. Let's go down to the bottom to 650. Very precise at 650. So it's probably, it looks like it's a little bit more linear at the bottom and then it starts losing it at the top. The way these guys used to do it, I think, is they would set the bottom and the top, and then they would actually draw the scale according to where the pointer marked on the different frequencies they sent. But these are, I mean, this is accurate enough for all practical purposes. And the result is we've done the alignment, RF alignment, both the oscillator and the antenna circuit for the medium wave. Now, for the long wave, it's exactly the same, except you'd set it to long wave. And then the signal you send is 210 kilohertz, and you adjust oscillator coil F and the front end coil G. Now, according to our drawing down here, we can see where F is, and that's for the oscillator to adjust it to the dial. But where's G? We can't see G anywhere on here. And this is where you've got to look a bit further, because G is actually on the actual ferrite antenna. You've got to shift it backwards and forwards ever so slightly till you get the peak reception. And that's for your antenna circuit. Now, as you can see on long wave, we only have one adjustment. We have to do F over here, that one there, and then of course the one on the antenna circuit. Okay, let's see where we are on long wave. I've got the signal generator producing 210 kilohertz. I've got it exactly on the blip at 210. There's a blip above, and there's that little dot there, that's 210. That's what they tell us to set the signal to. Oh, here we are. It's quite a little bit lower. It's at about 197. So what I'm going to do is I'm going to put this at 210. Exactly, I'm looking at it head on. You might see it slightly off on the camera. It's exactly at 210. And now I'm going to adjust the oscillator. Give it a bit of volume. There we go. There it is. I'm going to look at the dial and just rock it. Yeah, it's exactly at 210. So oscillator is done. Put the volume down. Now this gets a little tricky because you've got to move that guy. You've got to actually move it sort of backwards and forwards. Now if you touch it, it's going to affect the tuning. So you've got to do it with a stick or something so that you don't actually affect the reception, affect the magnetism around that. And the way I do that is just take a non-conductive stick or something, and then I can push it backwards and forwards. And I'll be doing that while I look at the meter. So, volume's up. That's a nice level to read at. I'll put that on dummy load. And now we'll watch the meter. And I'm not sure if we will see much. You see, if I just touch it, it's sort of affecting it. But if I move it, it's really difficult. It's going down. It's going up. I'm touching it. Whoa! Let me put the volume down. That has really made a difference. I'm pulling it out. Hang on. Okay, now it's going back. So I've got to go back a bit. There. That has really made a huge difference to the alignment or to the sensitivity of that of long wave. So we're done. For shortwave, we have again two markers. You select shortwave and you've got a marker at 6.1 megahertz, and for that you adjust oscillator coil H and front end coil I, and those are indicated on the schematic, H and I. So it is that guy over there, and I is that guy over there. That is at 6.1 megahertz. There is our 6.1 megahertz marker, that little blip on the top there. So I can dial into 6.1 megahertz. It's, as I said, I'm looking at it head on. You're not, but it's exactly at 6.1 megahertz. Now, I need to change something here. Let me show you what I'm talking about. As I mentioned earlier, I've been injecting that signal, those signals for the long wave and medium wave, through a coil. And as you can see, I couldn't resist. I've been playing around with a 3D printer again. I'll show you at the end how I did this. This is the same coil, but it's inside a former and it looks nice. So I've been injecting it into here from the signal generator, and then this radiates it to the ferrite antenna core over there. This works well for long wave and medium wave. It does not work for short wave. For short wave, you've got to actually feed the signal into the antenna socket at the back, the AM antenna socket, that guy over there. Remember, there's the AM one below and the FM above. This goes into the AM, so it's going straight into the antenna socket at the back. But I've also got to change something over here. This is the switch attenuator. I've got the various attenuation switches over here. I'm not sure how much attenuation I will need. I will put the signal at minimum and see what we get. But I also have a dummy antenna switch over here, which brings a circuit in line with the signal between there through the attenuation switches and there. It brings that dummy antenna in to make this signal generator signal look like an antenna in terms of impedance. This is what they sometimes actually give the schematic for on some of these service manuals. So if it's good enough for them in the 50s, it's good enough for me now. I've got that switch on. I'm going to set this to 6.1 megahertz. Modulation is on, still AM modulation. The amplitude is at its minimum. I'll switch that on. Let's put the volume on. Oh. That is exactly on 6.1. Exactly, I couldn't make it closer. Put the volume down. Right, so the oscillator circuit is pretty well tuned, perfectly tuned. I wonder what the antenna circuit is like. Let's go and play with it anyway. It's on 6.1. I'll leave it on 6.1, so you'll see the effect of me adjusting some of those cores. Now, according to the instructions, the oscillator coil is this one over here. So we'll just listen to it. The volume high enough so we can hear it. I don't want to touch that. That's mains voltage over there. Goes off. Goes off the other way. I'll leave it exactly there. That's what you would adjust if you weren't on frequency. Now we need to adjust that one there for a peak signal. And for that, again, we'll look at the meter. When you look at the meter, I'll be adjusting that one over there. I'll put that on dummy load again, so we don't have to listen to it. I'll give it a bit more volume so we can see this thing going up to the center more or less. And now I'm going to adjust that front end coil, try and peak it. Aha. It goes down, going up again, goes down. So that there is our peak. And we've peaked the antenna coil at 6.1 megahertz. Good, that part's done. And then you set your signal generator to 17.9 megahertz, where you have another blip, and you adjust the front end trimmer, K, which is that guy over there. We don't have a trimmer for the top end of the band, the 17.9 megahertz. Let's tune to 17.9. Now 17.9, it doesn't actually have a blip, and that's probably why, yeah, it's probably correct, because we don't have an oscillator tuning adjustment at this point. With the shortwave, you only adjust the oscillator at the bottom end and sort of hope for the best over here. You only adjust the front end coil or adjustment trimmer for best reception. So let's see where we are. That's 17, that's 17.5. Not bad. That is just, yeah, that's 17.9. Bloody hell, that is exact. I'm impressed. I'm really impressed. Right, so now we've got to adjust for the best reception. So let's flip this over and see what we need to do. So the one I've got to play with is that guy over there. Let me show you the meter, and I'll be adjusting that as you look at the meter. Okay, same story. Dummy load. Give it some volume. Let's put it about halfway on the meter, that is. And now I'm going to adjust that trimmer for a peak. No, wrong way. Well, well, well. Okay, we've hit a peak. It's going down again. That is peaked. We've got a bit more out of that. And that's done. And those of you paying attention will probably remember that there's something else that I should have mentioned along the way. Every time you do an RF alignment of a band, you do the bottom, you do the top, but you have to come back and repeat. Rinse and repeat. Because when you adjust the top, it affects the bottom. When you adjust the bottom, it affects the top. So this is actually an iterative process. You improve it till you get it as close as possible to perfection according to the instructions. So on medium wave, you do the bottom, you do the top. When you come to the bottom, sometimes it's not quite there, so you adjust the bottom again. And when you do that adjustment, you've probably messed the top up a bit. So you go to the top, do it again, and you keep doing that until you can get no further improvement. Same applies with, actually with the long wave, it's not really the case because there aren't two oscillator alignments. Shortwave, same story. You align this trimmer at the top, you got to come to the bottom and make sure that it hasn't moved your alignment of the front end coil. It probably won't adjust the frequency at all because you haven't done a frequency adjustment at the top, but you do have to go backwards and forwards. So this version that I've shown you is the one way through, but you do have to rinse and repeat on every stage of the alignment to get this to perfection. And now we're done with all the alignments of the AM bands, the medium wave, the long wave, and the short wave. And this is it with this lot of controls over here or adjustments over here. These are actually very easy to work with. These trimmer caps are very good quality, and you can easily turn that. It's not in danger of breaking. These cores have not been stuck with masses of, of wax. So I didn't even need to remove wax. This is fantastic. These are little elastics. If you see that, that's an elastic. And what it means, I've just broken a piece off. What it means is that they made the core purposely loose inside the former, and they put a little strip of elastic in there to tighten it, to hold it in place. So when you adjust it, it sort of stays in place because the elastic keeps it there, but they haven't gone and filled it in with wax. When they do put wax in there, you've got to be extremely careful because you can break those cores. You've got to use a plastic or a weaker tool, weaker than your core, otherwise you'll break your core. If you break your core, you're going to have a very, very bad day. I've had many of them. I try to avoid them at all costs. So, adjustments done, RF alignment done, and I hope that this explanation has enlightened you to the mysteries of RF alignment, the fact that it's not really that much of a mystery, the fact that it actually makes perfect sense, and the fact that if you know what you're doing and why you're doing it, it makes even more sense. And you'll understand why I'm saying this when I move on to the FM alignment, which I'm not going to do today, because what I want to actually do with the FM is I want to stretch the dial. This thing goes to 100 megahertz. My favorite station is at 101.6. I want this thing to stretch to 101.6. And with the understanding of the logic and the theory behind, or the reasons behind the RF alignment that we do, I'm hoping that you'll understand how and why I can do that on the FM. But FM is for another day. AM is done. And I hope you've learned something, and I hope you've enjoyed that. And if you have, click like, share. Wait a minute. I promised something else. I promised I'd show you how I built that coil on the 3D printing that I've become totally obsessed with. Let me show you that quickly. This is that coil that I've designed and built, 3D printed. What I did was I went into Fusion 360 and I did this in two bodies. That section is one body, the bottom section is another body. They are stuck together with some screws on the underside. that go through, put a bit of glue in between there. The reason I did that is it's a lot easier to print. What I've done is I've created basically these two concentric rings have got a 3mm gap in between. I wasn't able to use that thick wire. I used thinner wire, which means I put a few more turns. This thing goes through there, comes out the bottom, and I've just simply created these banana sockets over here that I can then just plug in the antenna or the signal into. I created this hollow underneath because I wanted to leave the option of putting a weight on here in case this thing was too wobbly, but it's not. It sits perfectly fine over there. When it sits on the side of the radio, the ferrite antenna is right slap bang in the middle along this way. So the height is fine. I adjusted that height accordingly. And it's very, very simple. And of course, I've been using my Bambu Lab A1 combo that I received from Bambu Labs. This thing has proved to be incredibly effective, incredibly useful. I've been playing around with different filaments. The one on the top right, that gray one, is the one I used here. It's PETG. The others are PLAs. This thing makes it incredibly easy to just flip between different filaments. And as I get used to using the software and the printer itself, the quality is improving dramatically. I'm really pleased, really pleased. And this is what it looks like in Fusion 360. It's got the two bodies, the circle, the coil, and the base. There's the top section, and there's the base. Looking at the top section, the back end is hollow. It's got those the two walls, but with the hollow in between. And on the underside, it's got these holes here, one at the bottom, one at the top, one in the front, one at the back. The idea is that your wire goes in here, does the looping, comes out the other side, comes out here. These holes are to screw it onto the base. So that is what that looks like. The front side, which is that one, has got this rounded edge, just to make it a little neater, but it looks great like that. Now, let's look at the base. I created the base with this hollow section here, thinking I might need to put some weights underneath to keep this more stable. As it happens, I don't need it. These holes go through to screw to the underside. They are countersunk, as you can probably see there, because I don't want to use this long screw. These little ridges here, these little gaps here, are to put some feet on if I want. Those glue-on types. If I hide the loop, and we can look at this a bit more closely, what we've got here is the two holes where the wires will come down. They come down, round, and out. These holes are where the screw comes through to connect it to the loop. And here we've got this little section here where the two banana plugs go in. And that is it. That's simple as that. I then sent this to the Bambu Lab slicer, and it printed it out in two sections because it makes it a lot easier to print. I could print this facing down, and I can print this with the base facing down. So it makes it a lot simpler. I also did it in two separate prints, just in case something went wrong. I didn't waste a lot of time waiting for, you know, when you wait and you find something's gone wrong, then you got to start all over again. I did this in two different print settings, and I'm really, really pleased with the result. And I'm sure this thing's going to be useful in the future. So once again, I hope you've enjoyed that. And once again, if you enjoyed that, click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon, PayPal. Thanks for watching. Bye for now. And most of all, stay safe.